Hello, this is David Ullman. Today I want to talk to you about propulsion airframe interaction, also known as PAI. I want to give you a brief history and the potential for development with electric STOL aircraft. These are the aircraft I want to talk about today. Some are electric, most are not. The ones along the bottom are all electric, and I'll go through the history of how we got to where we are today. To give you some idea about what's possible today, let's consider the Little Cub. This is a custom-built airplane for the Valdez annual sSTOL, short takeoff and landing event. The goal here is to get off the ground and back on it again in the minimal amount of distance. What's important about the Little Cub is it has a very large wing area. It's very, very lightweight. Everything's trimmed down to the least weight possible. It has lots of power. The engine's probably nitrous injected, and it has high lift devices on the wing. Most of the lift comes from these leading edge cuffs that you can see on the wing, the rear flap, and the fact that the internal combustion engine, the propeller, is blasting air on the underside of the wing. If you want to consider takeoff distance, this equation is a fairly simplified one that you can use to calculate it, and it's dependent on the wing loading, which is the weight divided by the wing area. And in order to get a short takeoff distance, you want a really low weight and a really big wing. You want to raise the thrust to weight ratio. Little Cub does both of these quite well. And you want to raise the lift coefficient, the amount of lift generated by the airfoil surface and whatever else is associated with it. So the way to get short takeoff and landing can be very well explained by this equation. We're going to look specifically at the lift coefficient. So the propulsion airframe interaction concept says accelerate the air over the top surface of the wing in order to make it move faster to get a lower pressure and increase the lift. So the faster the air, the more the lift. Notice this is different than what the Little Cub is doing. For the most part, it's blasting air on the underside of the wing. It has the leading edge cuffs to try to get the air to move faster and stay attached to the top surface. But we're talking about purposely designing something to increase the airspeed over the top surface. The father of PAI is Willard Custer, and back in the 40s and 50s, he did a lot of experiments on this, and he came up with a saying, it's the speed of the air, not the airspeed. So here you can see Willard in about 1946 in his Custer Channel Wing number 2, and you can see where the engines are mounted, drawing the air over these channel type airfoils, and sure enough this flew quite well. And what he's doing is, even when the airplane's not moving forward, there's a high velocity air over the airfoil section giving him lift. And this is really shown very well in this photograph, where an empty Custer Channel Wing has its wheels off the ground. Now I did some calculations on this, and he had a headwind, but he's definitely generating lift equal to the weight of the aircraft. So here's the Custer Channel Wing in flight. You notice it has little stubby wings off the end. The story goes that the FAA forced him to add those before they'd consider it an airplane. And you can see it flies quite nicely. By 1953, Custer developed a 5-passenger, hence the CCW-5, out of a Baumann Brigadier aircraft with custom wings. And here you can see it taking off. Notice it'll immediately bank over. In a traditional airplane, you'd never do that because you don't have enough forward speed. You'd stall your inboard wing. And here you can see it landing. This photograph doesn't show a very good perspective on how steep the airplane is coming in, and lands on the ground and comes to a halt fairly quickly. By the 1960s, Boeing got interested in this and developed what's called the YC-14, and it has jet engines inboard blowing over the top surface of the wing so that it could get off the ground in a very short distance. This is a 170,000 pound, 7,700 kilogram airplane that could take off and land in 800 feet. A traditional airplane without these high lift capabilities would take 3 times that distance to get on and off the ground. And here you can see him landing. does his reversers, comes to a stop in a very, very short distance. By 1987, NASA QSRA has been developed, and it's got 2 jet engines inboard on each side, so a total of 4 engines. Here the QSRA is taking off. You can see he's off the ground already. To show off, he'll instantly bank over without falling out of the sky and execute a turn. And you can see the jet engines blowing air over the top surface of the wing fairly clearly here. And on landing, it'll become apparent in a second how steep he's coming in, and the airplane will come down and come to a halt in a relatively short distance. Wheels touch down, nose wheel down. He's going so slow, comes to a halt quite rapidly. From the QSRA final report, here's a diagram of lift coefficient versus angle of attack. For comparison, the 727 has a maximum lift coefficient of about 2.5. Remember, the higher the lift coefficient, the lower the length of runway needed to get off or back on the ground. You'll notice that the YC-14 has at least twice the lift coefficient. The QSRA has 3 times the lift coefficient of a 727, reducing the landing and takeoff distances proportionally. Another important feature here is that the angle of attack at which stall occurs, at which the airplane loses lift, is much, much higher on the 2 research aircraft, and also is much softer. If a Boeing 727 would stall, it would lose a dramatic amount of lift very rapidly, whereas these other aircraft would not. So if you look at this evolution I just took you through, Custer used IC engines in channels, the YC-14 2 jet engines, 1 on each side, QSRA 4 jet engines, and then we're doing an electric approach which tries to distribute the lift along the entire span of the wing. So we have a project called IDEAL, Integrated Distributed Electric Augmented Lift, which we're using ducted fans, actually they're model airplane ducted fans, to blow air over the top surface of the wing. And here's a test vehicle called the Jabberwock. It's based on a Jabiru aircraft that has just 4 of these on for test purposes, 2 on each wing. You can see from the patent drawing that we could distribute them along the entire span of the wing. That has not occurred yet. So here's a Jabberwock on a flyby. The IC engine is running. The 4 ducted fans will not sustain enough lift to keep the airplane in the air, but they're clearly enough to take good data. So by using propulsion airframe interaction for electric STOL, you can more than double the lift, you can decrease the stall speed, you can decrease the takeoff and landing distance, you can get improved low-speed handling qualities. This wouldn't be complete without mentioning the X-57 Maxwell that NASA is currently working on. They are using distributed propulsion, and they are getting propulsion airframe interaction, but they're primarily using it to augment the fact that they've got a much smaller wing, improving the cruise capability of the aircraft. Here, the 10 inboard electric motors all have the propellers folded because they're only used on takeoff and landing. So what's the future? The ideal future would be to replace the Little Cub with something else that has distributed electric propulsion. Currently working on ideas like that. If you're interested on the ongoing sSTOL work, look at the website. Thank you very much for your attention.